Hi everyone, so today I'm going to be talking about Cloudcast, which is about high-throughput cost-aware overlay multicast in the cloud. And I'm presenting this on behalf of a number of my collaborators at UC Berkeley in the Sky Computing Lab. So just to give a quick overview, since there's a lot to cover here, so in the first part, I'm just going to go over the context of the problem, multi-cloud, multi-region, bulk data multicast. And then I'm going to be talking about basically how we find high-throughput, low-cost replication trees for multicast, and also how we approximate finding these solutions. And finally, I'll talk about the system architecture and how we actually run these multicast transfers via programmable overlay routers. So to start off with, some of you are probably familiar with the concept of multi-cloud or sky computing. Basically, we're seeing more and more new cloud providers, and increasingly workloads are being run or migrated across multiple different cloud regions and providers. So examples of this include things like geo-distributed model serving, cross-organizational dataset sharing, and also just more generally, any kind of cross-cloud applications. So when you have this necessitates sharing data across multiple clouds. So for example, you might want to publish some model weights, share a data set, or have just generally application data that you need to move across these different cloud regions and providers. The problem here, though, is that replicating data across cloud regions, or even just within providers, both within regions and the providers, is both slow and expensive. So I'll go into this more in a bit, but cross-region egress can be up to 9 cents per gigabyte, and cross-cloud egress can be up to 19 cents per gigabyte. So these costs can very quickly add up. So going into this a bit more, what we basically looked at in this work is how can we optimize cost for cloud multicast. And bulk data multicast is, of course, as I'm sure many of you know, a very well-studied problem. But it's unique in the cloud setting for two main reasons. So first, we have resource elasticity. So this means that as long as we're willing to pay the dollar amount per second, we can elastically create VMs in the cloud to execute transfers. And second, we also there's a unique pricing model for the network in the cloud, which is that the network costs are per gigabyte. So historically, you pay for the network in terms of bandwidth. And so this is kind of what most optimizations focus on. But in the cloud specifically, it doesn't matter at what rate you send data. What matters is how much data in total you send. So we basically look at how can we minimize cost under a replication time SLO for cloud multicast. So here's a simple diagram of what a direct replication might look like. You have some source region in S3, and you're transferring data to other object stores and other cloud providers, as well as other regions. So the problem here, as I mentioned, is first of all, you have very expensive links. So you might have region pairs that cost up to 19 cents per gigabyte to transfer between. Second, there's also constrained source egress. So clouds will typically cap the bandwidth of VMs. And so because of this, you have a bottleneck at the source oftentimes. And finally, there's also low throughput connections. So we profile different region pairs and transferring between them in the clouds. And there's actually a lot of variability where some regions can be extremely slow to transfer data to or from. So going into this example more, basically this is a visualization of a source region in red transferring to 6 destination regions. So these are all real regions. So say the source is GCP North America Northeast 2A, and then we're transferring to a bunch of different regions, including in Azure, AWS, GCP, across multiple geographic regions. So these costs shown on the arrows, the cost can be up to 19 cents, but there is some variation. So you'll see some of these are 12 cents, some of them are 15 cents. So with this direct transfer, replicating data costs 90 cents per gigabyte. So this would be up to $900 per terabyte or $900,000 per petabyte. So this would be a high recurring cost to incur if you're regularly transferring data. But we can actually start to optimize this cost. So one very simple thing we can do is to go back to our intro algorithms class and run a minimum spanning tree. So basically create a graph that minimizes the total cost of edges, but still connects all the source and destination regions. So this actually gives us a 30% cost reduction to just 60 cents per gigabyte. And we can take this even further by using overlay regions. So these are the regions shown in white. So Azure, Canada Central, and AWS US West 2. So these are neither source nor destination regions, but routing through these overlay regions actually reduces the cost even further. So this is generated with something called a Steiner tree algorithm, which is very similar to the minimum spanning tree. You're just allowed to use extra nodes that are neither source or destinations. So this gets us up to a 47% cost reduction, but actually reduces the throughput. So this brings me into my second part, which is basically how do we find high throughput, low cost multicast replication trees approximately, since it takes a very long time to find them perfectly. So our method is basically the Cloudcast optimizer. So we define a MILP to minimize costs under a replication time constraint. So the output of this MILP is basically figuring out how we can route data by determining both the number of VMs to create in each region and also how to route multiple stripes across multiple replication trees. So each stripe is just a subset of data where different stripes will be assigned to different replication trees. And the inputs are the price grid and bandwidth grids. So the bandwidth we actually collect by profiling the cloud providers, and the prices we can actually scrape from the cloud providers' websites. And the application or the user will basically provide the job, which specifies the sources and destinations, and also the constraints, which is the replication time, SLO. So what's sort of unique about this problem, because I'm sure you've all seen MILPs in this context many times before, is that typically optimizers will determine the bandwidth per edge in terms of like what to actually optimize. But in this case, we have this cost variable, which is a function of the total volume of the data that's sent. And the total volume of data that's sent over an edge is the allocated bandwidth times the total transfer time. So this is basically a multiplication, which ruins the linearity of the MILP. Because basically for it to be a MILP, we need to kind of have the variables be linear. So our solution to this was sort of to instead formulate things in terms of volume of data rather than bandwidth. So these are A, B, and C this is just a simple example. Basically like stripes are subsets of the data. And we instead think of this as more of like a bin packing problem, where we have some source regions and the destination regions, and based off the profiled throughput of the edges, we basically figure out how many bins we have that we can place data into those bins. And similarly for the node bandwidth, which is basically the VM egress and ingress limits, we can create a similar constraint that we represent in terms of the total volume that can be sent throughout the time of the transfer. So this is an example solution. The source GCP is shown in purple and the destinations are shown in blue. So, we denote each edge with the stripe that's sent along that replication tree. So you can see that there's 5 stripes total, and the source only sends out 1 copy of the data. So this is very important because the source egress bottleneck is one of the biggest constraints in the multicast setting. And it routes through a bunch of different overlay regions and then basically makes sure that eventually all the data or every single stripe arrives at each of the destinations. So what's kind of strange about this example, and there's a lot of strange solutions that happen, is that stripe 3 is routed from GCP out to Azure and then back into GCP, which at first glance would seem very inefficient or wrong, but we looked very carefully and it's not wrong. So yeah, you get a lot of really strange solutions like this because of the pricing models of clouds. So one issue when we designed this MILP is that basically the solve time is far too long. So there's 71 regions and 5,000 edges, and we need to determine a replication tree for every single stripe. And so as a result of this, it's actually quite hard to scale this MILP even to larger numbers of destinations. So even with 6 destinations, the original MILP that we formulated took many hours to run. So I'll go into this plot later on, but this is like in the red box, the original with no approximations, the runtime of the MILP. It basically becomes untenable very, very quickly, even with a small number of destinations. So the first approximation that we did was basically trying to reduce the number of considered regions. So the intuition is basically, can we pre-select the important regions to consider to use as overlay regions for the transfer? And the idea here is that regions often share very similar features in terms of their bandwidth and costs in relation to other regions. And so they're basically equally useful to the optimizer, and we don't need to consider every single one of them. So we did this by basically clustering regions with similar attributes, and then sampling a single region within each cluster. And for our experiments, we found that about 20 samples from 71 total regions was pretty good, and this actually helped reduce the runtime a lot. We also added 2 more approximations. So one was the stripe iterative approximation, where we solve the MILP for a single stripe and then update the constraints accordingly and basically greedily optimize until we have no more stripes. And then second, we also had a hop constraining approximation, where we only considered a maximum of 2 hop overlay waypoint regions. So this is a graph showing basically like how the approximation, basically that we needed to combine all these approximations to get the solve time to be tenable. So this original no approximation MILP was, shown in purple, just very, very high very quickly. But even if you just use each of these approximations individually, you can see that basically once you get to like 20 destinations, they're all taking a really long time. Like 1,000 seconds is way too long to be running this optimization for. And it's actually crucial to combine all of these to get the solve time to be within the range of seconds, which is what we want for this to be practical. With this, solve time in a couple seconds. So finally, I'm going to go over our system architecture. So basically, how we ran overlay multicast with programmable overlay routers. So this is an overview of our system. Basically, we have a client. You can use both a Python client or just a CLI tool. And you'll specify a source path, which is an object store path, and also destination paths, which are also in object stores. And then in addition to that, you also specify some replication time constraint, so something like 10 minutes. And so then this is then passed to the control plane, which in the code includes the price grid and bandwidth grid that I mentioned before. And then all this information is passed into the planner, which basically runs the algorithm that I just described to you all to generate something called a router program, which I'll go into more in a second. And this router program is basically passed to each of the VMs to tell the VMs basically how they should route data. And the provisioner is responsible for creating VMs in the cloud and passing this router program to each VM. And finally, once the transfer is started, we have a status tracker that will basically monitor the progress of the chunks of data running on this overlay network and determine when the transfer is completed. This final part on the bottom is what we refer to as the data plane or the overlay network. So basically, cloud VM, a cluster of cloud VMs that's reading from object stores, sending data between VMs, and writing to object stores. So this cloud overlay network, as I mentioned, is created by creating a sort of ephemeral cluster of VMs, which we refer to as overlay routers. So these spin up pretty quickly in about 40 seconds and also auto-terminate and basically run a Docker container that processes, can read and write from object stores and contains all the code that we need to run Cloudcast. These overlay routers are basically responsible for executing the transfer by reading, sending, and receiving data. So one challenge that we had is basically how do we encode this overlay router behavior. So we want to be able to specify these replication trees, and we also want to make sure that like different chunks of data are handled in different ways so that we can basically have multiple replication paths. So we did this by defining something called a router program. So our planner will basically write a router program for each VM, and it specifies, given some data, how should it process that data. So the operators are things like reading and writing from an object store, receiving and sending to other overlay routers, and also like a or and and. So in this example DAG, you can see that the way it should process data is to read from S3 and then to both send to 2 IP addresses. And in order to support striping or basically having different paths through the overlay network, we had something called a routing ID, where each routing ID is mapped to a specific DAG. So you can have multiple of these DAGs on each VM. And depending on when it receives some data, it'll be marked with a routing ID, which will tell the VM exactly what it should do with that data, or that data identity. So finally, I'll go into our system evaluation results. So all the details about our baselines, there's a lot of baselines, and how they're adapted to Cloud Multicast are in the paper, but I'll just quickly go through the sort of major ones. So there's obviously direct, which is transferring from one source to each destination directly. There's also the minimum spanning tree and Steiner trees, which I mentioned at the beginning. So basically these classical algorithms for building minimum cost trees. And we also compared to inner data center multicast algorithms and also some prior work on Cloud Unicast and Multicast, which is prior work like Skyplane and Cloud MPcast. So this is to start with a simulation result that we did with a bunch of different data points. So the line in purple is the Cloudcast sort of Pareto curve of cost versus replication time. So as I mentioned, the optimizer can take in different replication time constraints. So for this result, we basically entered a bunch of different constraints to get this like curve. And we did something similar for Cloud MPcast and Skyplane to also get sort of similar curves. And you can also see that the direct is basically much more expensive and slower than many of the solutions that we get with Cloudcast. And the Steiner tree and minimum spanning tree solutions are relatively cheaper, but still much slower compared to Cloudcast. And Deadline, Aware, and Spider are both work in inner data center work that optimize throughput. So you can see that their throughput is pretty good, but they fail to minimize costs because they don't have that cloud awareness. So we got very similar results with just some fewer points for our full system experiments. So this was an inter-cloud data transfer we ran from one source to 6 destinations across GCP, AWS, and Azure. And yeah, as we saw in the simulation results, we get up to about 62% cost reduction and 2.8x speed up. So yeah, very similar results in terms of where Steiner tree, minimum spanning tree, and direct solution are located in the graph. We also ran experiments just within clouds. So this is basically transfers running within a cloud, but across multiple regions. So the results are sort of less dramatic in these cases because there's a smaller optimization space. But you can actually still see that even for intra-cloud transfers, Cloudcast has much lower cost and better replication time than other baseline algorithms. And finally, one more thing I wanted to mention is basically the more destinations we have, the more optimization opportunity there is. So you can see on this side, yeah, the cost reduction side, basically as you get more and more destinations, the optimization space gets bigger, so you can basically get more dramatic cost reductions. And similarly, for replication time speedup, the more destinations there are, the more replication time speedup you'll get. And we got these numbers by basically randomly sampling destinations and sources to simulate running transfers through. So yeah, just to kind of wrap up, the Cloudcast implementation is available inside of the Skyplane open source repository. So we actually implemented this system as an extension to Skyplane, which was published in NSDI 2023. And currently we support multiple clouds such as GCP, Azure, AWS, and Cloudflare. So yeah, that's all I had for today, and thank you everyone, and happy to answer any questions.